So today I've got a brand new puzzle for you. This one was sent to me by Andy around about 2:30 yesterday, which took me embarrassingly until about 6 o'clock to complete. My excuse is that I was trying to do my day job in the middle of it, and when 4:30 came along, I was left with an hour and a half to solve the puzzle as I wanted. Again, for anyone who is at my level of maths, you're going to see that that was a rather embarrassingly long time. Excuse number 2 is that when I did solve it, I wanted to be convinced. So I'm going to try and convince you that it took me about an hour to convince myself that I got the right answer, rather than spend an hour and a half banging my head against the desk. I didn't do that. That's a health and safety warning right there. Don't ever bang your head against the desk to solve a maths puzzle, but do take the time to confirm that you've got the right result. It's a really satisfying moment when you know that you've got the correct result. Anyway, I'll give you this puzzle and I will tell you now it can be solved with GCSE Maths. It is a migraine to do it that way. It can also be solved with some slightly more advanced maths, and I don't consider it cheating if you solve this using Microsoft Excel or any other program with Spreadsheet function. So the puzzle that you're looking at, I have not really very inventively named it 9 tokens. Why? Because what you can see here are 9 tokens. 4 of them have the value of 4, 1 with the value of 3, 2 2s and 2 1s. The idea is that in some hypothetical game, there are 3 players who are given 3 tokens each, and they're given out randomly. What is the probability that player A has tokens whose value is greater than or equal to 10? Can you do it? To begin with this puzzle, you could start immediately by thinking about all the possible different combinations. You could start by thinking, what happens if I add 1, 3 and 4? What if I add 4, 3 and 2? What about if I had 4, 4 and 4? You can start to give yourself an absolute list of all the different ways of solving it. And some of you will have done that. I certainly did. And then you realise, before you've even started, there's a lot of information to manage. Can you figure out the probability of getting a 1 and a 1 and a 2? What about the probability of a 2 and a 3 and a 4? What are all the different results and what's the probability of getting each of them? That is a way to approach it. And if you're sat there having paused this video with several A3 sheets of paper, you've run out of paper and you've continued the writing up the wall, you will eventually get to a result. That doesn't seem the most elegant, and I wouldn't be surprised if any of you abandoned that protocol at this point, and I wouldn't blame you either. So the first thing is to consider might be, what's the maximum value that we can get from this working out? What's the from these tokens, what's the biggest value we can possibly hope to achieve? And you won't be surprised to realise that that is 4, a 4 and a 4. So the maximum score that anybody could get from being randomly given these 3 tokens is 12. Now that's interesting because that's not much bigger than our maximum value. So what else could we get? Well, the next highest score would logically have to be 4, 4 and 3, which would give us 11. And after that we can make a fairly quick leap to see that 4, 4 and 2 would give us 10, which tells us right from the off that we've already got a very narrow range that gives us the result that we want. You could try playing around with this. You could try and find any different combinations that would give you the result that you're after. So you could say, well, what if I upped the 2 to a 3? So 4 plus 3 plus... well, you'd need another 3, which is problematic because we've only got 1. So it doesn't seem like much of a help to begin with. But what's really useful is that we'll note with this puzzle particular, or this layout of tokens, these are our only set of feasible results. The 4, the 4 and the 3, the 4, the 4 and the 2, and the 4, 4, 4. Now, most of you will have figured that at home without too much of an issue. So, okay, what's the probability of picking a 4 and a 4, 4, 4, 3, and 4, 4 and 2? Does that make the problem seem a little bit less nightmarish? Probably not, because what I suspect most of you will have jumped straight onto are probability trees. What you are looking at here is precisely the reason that I'm not overly fond of using probability trees for this puzzle. It will work, and I have absolutely no doubt that many of you will have gone for an A2 or an A0 to create a probability tree. Why? Because we have to enlist, for a complete probability tree, we have to enlist all of the different results. So we have to include the probability of getting a 1, a 2, a 3, a 4. Then we have a second branch. What happens if we get a 4, 3, 2, and a 1 from that? Again, you will get the right answer, but that's just a horrendous amount of working out. So what you've got here is a slightly more simplified probability tree. Why have I done it this way? Because to begin with, you'll notice there's a complete absence of 1 from any of the options. If you try and find any combination of 1, you'll notice it's going to give you nothing like the right answer. Sorry for that slight distraction, I'm just making sure that the sound's off. If I had a 1, for instance, then the maximum we could get from that is 9. Why? 1 plus 4 plus 4, that would give us 9. There is no way of getting a score greater than 10 using 1. So you'll notice in the probability tree, what I've done is I've not even thought about 1 anywhere in the screen. I don't bother to use it. Now, coming up here in this top half, in this top section, you'll see we've got all the different combinations. And in some sets, I've just stopped. I've stopped my branch of working out entirely. In the second branch, what I've done is include the total. So if I had 4 plus 4, I'd get 8. 4 plus 3, we'd get 7. And 4 plus 2, we'd get 6. And then over here in the top section, what happens if I get another 4? Then that would give me 12. If I added 3 there, I'd get 11. And if I added 2, I'd get 10. Coming back from the second branch, 4 plus 3 gives us 7, plus another 4, that would give us 11. And if I got anything other than 4, as in if we got 2, then we'd only have a score of 9, so I haven't even bothered to figure out those probabilities. And we can carry on with that as we go. Coming down into the second main branch, we've got 3 plus 4, which would give us 7. If I got a 4 at that point, then I'd have 11, and if I didn't get a 4, well, there's no point figuring it out. If I didn't get a 4 after the 3, again, there's no point figuring out, and so on. Coming down to the 2, it's pretty symmetrical. I could add 4 to get 6, or anything other than 4, we might as well stop. From that, we get an absolute load of probabilities, absolutely loads of them. What do you then have to do? Figure out the probability that each branch gives you the result that you want. Now, you could do that if you wanted, so let's have a look at the top branch here. We've got a 4, followed by a 4, followed by a 4. I shouldn't have used a multiplication symbol there, but it's fine. So the probability of that, well, that would be we have 4 4s to begin with out of a possible 9 tokens. Following that up, we then have 3 4s left over out of 8 tokens, and then finally we would have 2 4s to choose from 7 tokens. You can do the mathematics if you want from that. Thankfully, I have a calculator that gives it to me. 4 times 3 times 2 divided by 9 times 8 times 7, and that would give you a probability of 1 in 21. And you can do all of those calculations and you will ultimately get yourself to the right answer. Assuming that your probability tree didn't fall apart or you didn't make any slight numerical error, you've only spent about half an hour on the problem at this point. And you can see it gets absolutely mad. So we're going to abandon probability trees, and I'm going to let you have a look at it a different way. I want to clarify something very quickly here. I'm not abandoning the probability trees just because you've increased the chance of a numerical error or because it's too hard. It's just a lot of computational work. And one of the things about mathematics isn't just doing loads and loads and loads of sums for the sake of it. Yes, it's important that you practice sums in school because you need to bury it up here. Repetition helps something to ingrain itself in its memory. Dancers can tell you that they rehearse for those reasons. An actor can tell you that they rehearse the lines regularly to get a feel for the emotions and the lines themselves. The more you practice something, the more it commits itself up here. But just actively doing the maths, once you understand it, once you know it, and you're always getting it right, that's pretty redundant, and isn't, to me, what maths is about. It's about looking at things from a different perspective, looking at new ways of doing it. With that in mind, let's have a look at the way we could have done it on a computer. So what you can see here is, well, basically a spreadsheet, and a very basic one at that. I've set up these, what are known as token values, so I've labelled it token 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then in here, I have all the values that are actually given. That's because I'm working towards what's known as a general solution, which I haven't got to yet. I am working on this as a fun side project, and if any of you have any ideas about it, please do leave them in the comments. Other than I'm a nerd and I'm spending way too much time on this puzzle, that's what I do. I'm setting the scene so that we can A, change the numbers as and when we like to solve a general problem, but also to let the computer do the hard work. The computer's going to do all the work that we otherwise would have been doing. What some of you might have done is try to say, right, well, here's all the different possible results. What are the ones that I want? So say, for instance, what you might have done to begin with is something that looks like this. Now, what I've done here is named all of my different possible combinations. So we could have had token 1, 2, and 3. We could have had token 1, 2, and 4. We could have had token 1, 2, and 5. Now, you can't see it here, but what I've done is written in some very particular code. What I've done is, if I'll copy the code out for you, in row G, which you can see highlighted at the minute, oops, shouldn't have done that, I've written the following code, so you'll be able to see it written in here. Or you should be able to. I have absolutely no idea why you can't see that. If I turn it... There we go. There we go. It helps if you put the text in a code that people can read. I've written that if G2, that is that cell here, if that doesn't equal 9, then this cell down here equals the cell above plus 1. Otherwise, it equals the cell to the left plus 2. Why is that? Because what you'll see is rather than list all of the different combinations out, rather than list every single set of numbers, and trust me, I did make a mistake trying to do it that way, and it was so hard to search for, what you'll see is that as we go down the cells, so I just dragged the cells down because Excel can do that for you, it can copy it and update itself intelligently, you'll notice when we get to 9 here, so this is a combination of tokens 1, 2, and 9, it then chooses to go up a bit. So what I've done is say I had combinations 1, 2, and 3, 1, 2, and 4, 1, 2, and 5, 6, 7, 8, and 9. And what's the next sensible combination after that we haven't already looked at? Well, that would be 1, 3, and 4. So what my coding got me to do here was say, right, well, we've got up to 1, 2, 9. What's the next number I can go to? Well, it's this one plus 2. 1, 3, and 4. Similarly, this column is designed to say, once we've run out, once this cell up here is equal to 9, this one's going to have to increase itself in value. So we've gone from 1 and 2, 1 and 2, 1 and 2, 1 and 2. Oh, the last one was 9. I now need to update to 1 and 3. And as we scroll down, you'll notice, yes, there are some, I admit, that are written in yellow because I didn't know how to manually update this left-hand side using logic. So far, I have the following for you. So far, what I have as updating itself is concerned is that formula. It's an if-or statement, and it gets pretty fuzzy, and if you're up to date on logic and you enjoy this sort of stuff, by all means, do send me the code that gives me a manual list taking us all the way through the combinations. It's also really kind of, I think it's quite beautiful how the number of changes that I had to input manually, they get a lot closer together. You can see an element of logic in that. It's almost like an exponential decrease. And I think once I see the pattern in that, I'll be able to update it all for myself. Again, this is the beauty of maths. You're playing with logic. I think mathematicians and computer scientists get on incredibly well with each other because they're both playing with a different form of logic, framing the problem, using the tools that we're given. And if we aren't given a tool, we make one for ourselves that obeys what we're doing. So anyway, I digress. What I've got here is a complete set of all the different combinations. If you wanted, say, tokens 4, 5, and 3, we could reorder that to 3, 4, 5 in ascending order, and there you have 3, 4, and 5. What about 2, 7, and 8? 2, 7, and 8's in there, that's going to be towards the start. It's sat right here. What does Excel then offer us? That offers us what's known as a lookup table. Now, I'm just trying to get rid of that because I know full well I've hidden some of the values that I shouldn't have hidden. What I then do is incorporate what is known as lookup. So lookup, again, a very powerful tool. What that does, I'll give you the coding there. The coding in lookup allows you to look up a particular table. So it says, well, in, say, for instance, here, I wanted token 1. So it looks up token 1 and says, right, well, what was the value of that? It was a 4. So it returns the value of 4. Why is that incredibly handy? Because, again, I don't have to manually input all the data. And let's say I were to change this value of this token to a 7. You'll notice all of my tokens turn to a 7 here. I'll undo that. What if token 3 was actually now worth 10? suddenly all my values become 10 where token 4 should have been, and so on. So it's a really handy trick that just makes the job a lot quicker. This is a computational method. What can we do now? We can turn all of the values to black. That should not be the thing here, but it does give me a nice little segue to show you how it was done. Equals the sum of the 3 columns to the left. Done. You can see there, 4, 4 and 1, that gives us a total of 9. We're then using a little bit more code. I will drag you over and you'll be able to see we have this box here. What I have thrown in is a formula that helps me count the number of sum values that are greater than or equal to 10. And from that, we get that there are 22. Of these 84 unique combinations, 22 of them give me a result that I'm happy with. So 10 or 11 or 12. I haven't gone through this list manually and added everything up as I've gone along. I've let Excel do the hard work. How many of those combinations did I say there were? There were 84, so what's 22 divided by 84? 0.261905. And that's just a decimal value. I'm not overly keen with a decimal value. There's nothing really that we can do with it. Now, most of you will have already figured out where 0.61905 came from, and that's absolutely lovely. Let me give you a few tools first that show you how to make it more elegant. So, folks, before we move on to the grand finale, I'm going to introduce you very quickly to 2 new bits of mathematics. They are factorials and combinations. They're new if you're a GCSE student at the very least, or if you're partway into your A-level maths course. Otherwise, they probably won't be that new to you. The first one, factorials, I'm going to introduce you to you right now, and combinations in a couple of minutes. Factorials are a lovely little tool. If you look on your calculator, if you've got a scientific calculator at home, you'll notice the button that looks like this, exclamation mark. A very exciting X. Actually, it does do something quite exciting. If you put 3 factorial into your calculator, or even into Google or Wolfram Alpha or whatever, you'll get an answer of 6. If you were to put 5 factorial into your calculator, then you would get 120. Now the question is, why is that? What has the calculator actually done? You'll notice that 6 is 3 times 2, and why not times 1? That seems fairly trivial, doesn't it? Well, what about 180? You'll notice, 120. That is in fact 5 times 4 times 3 times 2 times 1. There you go. That is what a factorial does. It takes all of the whole numbers, including the one that you have written in, and multiplies them. So if you were to do something like, say, 7 factorial, you get 7 times 6 times 5 times 4 times 3, 100 factorial, which is not going to be as easy to just work out with pencil and paper. 100 factorial, 100 times 99 times 98 times 97, to 321. It multiplies them all up and gives you a nice little answer. That's factorials. Dead easy, yeah? What we have then is combinations. Now, what are combinations useful for? They're a way of saying, you've given me this many people, how many different ways are there of choosing 2 of them? Say, for instance, I've given you 7 stickmen here. Let's assume that they're going for a rugby team, and I need to choose 2 of them. How many different ways are there of doing that? Well, let's look at a slightly bigger picture to begin with, shall we? Let's say I wanted to know how to choose all of them. So, how can I order them in any way I want? So I might want 4, 5, 6, 7, 1, 2, 3. I might want 2, 4, 6, 1, 3, 5, 7. Take your pick. I might want 3, 1, 4 as the best approximation to pi. I don't know. To begin with, if I put them in order, then I have got 7 choices for my first person. There's 7 people, I've got 7 choices. But if I've already chosen my first person, say person number 3, I've only got 6 choices left. So once I've made my second choice, I then only have 5 people left. After that I've got 4, then 3, then 2, and then, finally, once I've chosen my first 6 people, I've only got 1 person left. Now that is looking a lot like 7 factorial. But again, as I pointed out, I only want to choose 2 of them. So I need to reduce this. Because I'm only really interested in my first 2 choices. Which means that I've got 7 times 6 choices, surely. So did I need to go through all of that? Well, actually, we can just neaten that up. We can get rid of the other 4, basically just by cancelling it out in this lovely little fraction. Why? Because this is 7 factorial now over 5 factorial. But what's the problem with choosing these two people? What if I'd chosen person number 4 first, and then I'd chosen person number 3? Is that any different from what would have happened if I'd have chosen person number 3, and then person number 4? Well, how do I compensate for that? The number of people I've chosen, I cancel that out as well. But that, in this case, is just 2 factorial. Now, if you put that into your calculator, you get precisely the number of different combinations for choosing your number of people. Your calculator will do all of this for you in the button N Choose R. If you look at that in your calculator, if you were to type in, say, 7 choose 2, your calculator will do all of that maths for you and tell you the answer is 21. There are 21 different combinations if you were to select 2 people from a grand total of 7. They are the 2 tools we need, and it's not very hard to imagine, say, for instance, if I am given 9 tokens and I want to choose 3 of them, how many different ways are there of doing that? From there, maybe we can find the probability of getting what we want. So here we go, onto the solution and the very mathsy one. You'll notice, by the way, I am so confident that the way we can solve this with the tools I've just shown you will take so little space. I've actually included the original puzzle as well. So, let's get on with it. The first thing we want to think about is how many different ways could we have received 3 tokens out of the grand total of 9? And with the trick I've just shown you, that becomes something that your calculator will do for you effortlessly. That is 9 choose 3, which will tell you there are a grand total of 84 ways. That is the total number of ways of picking 3 of these tokens from the original 9. Why is that quite cool, do I think? Because what you'll notice is that if you go back into the section on the Excel, there were 84 unique combinations. Now, we would have had to build that, even using the code, that takes a little while, whereas the maths will tell you like that. So now, what else do we need to think about? Well, we had several different sets. We had 4, 4, and 4, because that gave us a total of 12. Remember, we wanted 10 or more. We had 4, 4, and 3, for a combination of 11, and we also had 4, 4, and 2. So what can we do with that? Well, first off, we need to know how many different combinations there are. What you'll notice I've done is I've given each of my little tokens a name, just to sort of help you understand what's going on. So I've called that one, say, 4-1, 4-2, 4-3, and 4-4, etc. Because what I want to know now is, of this smaller section, how many different ways are there choosing, say, 3 4s from 4 of them? And that you'll find is 4 choose 3. As in, I've got 4 and I want to choose 3 of them. Now, if you put that in your calculator, you'll probably be not that excited by the result. There's only 4 ways of doing it. But you can think about that as, say, rather than choosing 3 of them, rather than going, right, well, I want 1, 2, and 3, or 1, 2, and 4, I want 1, 3, and 4. What you can think about it is, how many ways are there of rejecting one of them? Because if I've selected 1, 2, and 3, I've gotten rid of 4. If I wanted 2, 3, and 4, I've gotten rid of token 1, and so on. So there's 4 ways of doing it. Let's think about 4, 4, and 3. So I've still got my original 4 big tokens, but I only want 2 of them now. I only want 2 of the 4s. And then we can multiply that by, well, I've only got 1, 3, and there's only one way to choose one object. So that becomes 4 choose 2. You'll find that that gives you 6. There are 6 ways of choosing 2 objects out of an original 4, multiplied by that 1 to give us 6. And finally, 4 choose 2, that's 4 choose, 2 4s and a 2, that's 4 choose 2 again, multiplied by how many 2s do we have? We've got 2, and I only want one of them. So I could have, say, for instance, the first 2, or I could have the second 2. 2 ways of doing that. Which means that this option has a grand total of 6 multiplied by 2. The calculator will do all of this for you to get 12. Last bit, we're on the home stretch. We therefore have a total of 4 ways to get 12, 6 ways to get 11, and 12 ways to get 10. That gives us a grand total of 22, and I'm going to do this in a different colour because I'm really excited at this point. 22 out of the grand total of 84 different methods That, fine, fair enough, will simplify to 11 over 42. And if you were to check that on your calculator, as sure as Excel gave us, after a good hour or so's worth of work, we get the result 0.261. 9047619, but I think it looks a heck of a lot neater as 11 over 42. And there you go. A puzzle that admittedly took me about 2.5 hours to finish, and it took us about 2 minutes of maths there. So there you have it. A puzzle that can be solved in 3 different ways. If you do it in GCSE form, then sure, it'll only take you about 3 hours. If you do it on an Excel spreadsheet, then fine, it might take you about an hour. And if you do it using a slightly advanced bit of mathematics, it takes you about 2 minutes, if that. Again, it's one of the things that I love about maths. You can always be satisfied about the results that you've got. You can convince yourself it's true using loads of different techniques. Me personally, one of the things that I love about maths is there's this lie going around that in maths there's only ever one right answer. Now, that might be true to a level, but there are always different ways of getting to the answer. And I think that creativity that you can have when you acquire more mathematical tools really is beautiful. Yes, my best friend, shout out to Chloe, said, have you really spent 2.5 hours on this, you absolute nerd? The answer is yes, I am. No, I'm not sorry. And it was a really good laugh doing it. And yes, very, very satisfying to look at all the different ways of doing it. So big shout out to Andy. Thank you so much for giving me this puzzle. If you have any similar at home that you want to look at, by all means go for it. If you want to look at the Excel coding, or if there's anything similar that can be done or anything like that, please do give me a shout. I've given links to some of the other videos that talk about combinations and permutations that I really like. Matt Parker and Stand Up Maths and Numberphile, they've got loads and loads and loads of different things that talk about combinations, permutations, probability, you name it. Otherwise, that's it from me. I hope you have a fantastic day. Enjoy the maths.